హలో స్టార్ట్ చేస్తున్నా. ఓకే ఓకే Good evening, everyone. Let us do some basics of this chapter, permutations and combinations, before we dive deep into the topic. So, let us first discuss some few basic concepts. So, the number of permutations of n dissimilar things taken r at a time, the number of permutations of n dissimilar things taken r at a time is given by as NPR. Of course, I am not talking about the fundamental principle, that is, if a particular operation can be performed in n ways and another particular operation can be performed in n ways, the entire operation can be performed in m into n ways. So, that is basic rule. That is, if the conjuncture and comes, replace that with an into symbol. If or comes, if the conjuncture or comes, replace that with a plus symbol. So, that is the basic principle, fundamental principle. The next thing is the number of permutations of n dissimilar things taken r at a time is NPR, and NPR is given by n factorial by n minus r factorial. Next, the number of permutations of n things are taken all at a time, is given by n factorial taken all at a time when p things are alike of one kind, when p things are alike of one kind, two things are alike of a second kind, etc., is given by n factorial by p factorial into q factorial into r factorial and so on. So, where there is a repetition of the objects, so the number of ways in which we can arrange them is n factorial by p factorial, q factorial, r factorial, etc. Next, if suppose there are n different things and if you want to arrange them circularly, then that is n minus 1 factorial. So, the number of circular permutations of n dissimilar things, the number of circular permutations of n dissimilar things taken r at a time is n minus 1 factorial. When the clockwise and anti-clockwise directions are not considered distinct, suppose we are not worried about the clockwise and anti-clockwise directions, that can happen in the case of flowers or colored beads which are strung to a string to form a garland. In that case, the clockwise and anti-clockwise directions will not be considered distinct. In that case, the number of circular permutations will be half into n minus 1 factorial. Next thing is the number of combinations, that is just selections, and the internal arrangements are not required in the case of combinations. The number of combinations of n dissimilar things taken r at a time is NCR, and NCR is given by n factorial by r factorial into n minus r factorial. These are the number of combinations of n dissimilar things taken r at a time. And NCR is equal to NCn minus r. A very useful result. NCR is equal to NCn minus r. And another thing is NCR plus NCR minus 1 is equal to n plus 1 CR. NCR plus NCR minus 1 is equal to n plus 1 CR. This is another result. And the next, suppose we have p things are alike of one kind, two things are alike of a second kind, and r things are alike of a third kind. If you want to select any number of things by taking at least one thing from the total, then the number of ways in which that can be done are p plus 1 into q plus 1 into r plus 1 minus 1. This is the number of ways which in which you can select any number of things when p things are alike of one kind, q things are alike of second kind, and r things are alike of yet another kind, which is p plus 1 into q plus 1 into r plus 1 minus 1. This particular formula we will be using for finding the number of divisors of a given number and few other applications. So these are the basic things and a few more selections and distributions, equal selections, any kind of selections, any equal distributions, any kind of distributions. Those things we will be discussing a little further later after doing some few problems on the basic things. So we'll start with some problems. A gentleman invites 13 guests to a dinner and places 8 of them at one table and remaining 5 at the other. Okay. The number of ways he can arrange the guests. So there are 13 guests and he wants to place 8 around one table and remaining 5 in around another table. Both the tables being round, circular. The number of ways he can arrange the guests. So first thing is, we have 13 people. Out of these 13 people, if I select any 5 people and ask them to go to the smaller table, the remaining 8 would automatically go to the bigger table. So it is a question of first selecting 5 people out of 13 people, which can be done in 13C 5 ways, or you can say 13C 8, anything you can say. Now that we have 8 here, 5 here, these 8 people can AND. When you say AND, it is into symbol and multiplication symbol, and these 8 people can be permuted around the circle in 7 factorial ways, and these 5 people can be permuted among themselves in 4 factorial ways. So the required number of ways are 13C5 into 7 factorial into 4 factorial. Right. So you can make some simplification and arrive at the answer. So here this is 13 factorial by 5 factorial into 8 factorial into 7 factorial into 4 factorial. So you get 8 here, and this 4 factorial goes here 5 times, and you get 13 factorial by 40. So 13 factorial by 40, so option D comes correct. Okay. Now let us see the next problem. If 8 persons are to address a meeting, then the number of ways in which a specified speaker is to speak before another specified speaker. See, there are 8 people, and it is the question of filling up of 8 blank spaces. It is a question of filling up of 8 blank spaces. 1, 2, 3, 4, 5, 6, 7, 3, 1, 2, 3, 4, 5, 6, 7, 8. It is a question of filling up of 8 blank spaces. Out of these 8 blank spaces, a particular speaker always wants to speak before another particular speaker. So that means there are 2 speakers, let us say A and B, and A says that I should speak before B speaks. He doesn't have to, they need not speak one after the other immediately, but the condition is that A should speak and B can speak anywhere after that. So for this, what you can do is first select any positions of the 8 positions. Out of the 8 positions, select simply any 2 positions. So any 2 positions of the 8 positions can be selected in 8C2 ways. So whenever you select 2 positions, one position comes first and the other position comes next. Whatever the position that comes first, let A take that, and whatever the position that comes next, let B take it, so that A is always before B. And in every case, there are 6 more positions, and the remaining 6 gentlemen who have no conditions, they can take those 6 positions in 6 factorial ways. So the answer is 8C2 into 6 factorial, and you can make the simplification and identify the answer. So I repeat once again, there are 8 positions, and out of the 8 positions, select only 2 positions. That can be done in 8C2 ways. So whenever you select 2 positions, it can be first and second, it can be first and third, it can be second and seventh, whatever. If it is second and seventh, the second position is taken by A and the 7th position is taken by B. So that A is always before B. So like that, out of the 8 positions, you are selecting simply 2 positions, and whatever the position that comes first in that selection, let A take that, and whatever the position that comes next, let B take that. So it is, that can be done in 8C2 ways, and in every case you have 6 positions that are left out, and the remaining 6 people can be filled in those 6 positions in 6 factorial ways. So the answer becomes 8C2 into 6 factorial. You can make a simplification, right? And deliberately I am doing one more problem on the same idea. Now the idea is extendable basically. Actually the same problem can be done in 2 different ways also. You have 8 factorial ways in which you can, the earlier problem if you see once again, there are 8 factorial ways in which we can place the people. Half the number of arrangements are such that A comes before B, and half the number of arrangements are such that B comes before A. So we want A comes before B. It can be 8 factorial by 2 factorial. Even that also can be said. So here 10 people are there, and there are 3 speakers A, B and C, and here instead of 2 people now there are 3 people A, B and C, and these 3 people should occupy 3 positions in such a way that A should speak before B speaks, and B should speak before C speaks. A, B, C need not speak one after the other consecutively. There is no need. Let A speak, B can be anywhere after that, and C can be anywhere after that. So the same idea again comes. Out of the 10 positions that you have, you simply select any 3 positions in 10C3 ways, and those, whenever you select 3 positions, there is exactly one way where A takes whatever the position that comes first, let A take that. Whatever the position that comes next, let B take that, and whatever the position that comes next will be taken by the C, so that A comes before B and B comes before C. And in every case, we are left with 7 more positions, and those 7 more positions can be filled with the remaining 7 people in 7 factorial ways. So you can see this is 10 factorial by 3 factorial into 7 factorial into 7 factorial. You can see this 7 factorial is cancelled. This is 10 factorial by 3 factorial. The reason is, if you consider, the same thing can be argued this way also. See, there are 10 factorial ways in which we can arrange the 10 people. Now, there are every block of 3 factorial possibilities where A comes before B, B comes before C, like that. So in that, every 1 by 6 of the total arrangements is the favorable arrangement for us. So it is 10 factorial by 3 factorial. So we can even generalize this. If suppose there are n people, and if n people have to address a meeting one after the other, and if there are r people who wants to address in such a way that A should come before B, B should come before C, C should come before D, and so on, then the number of ways in which we can arrange them will be n factorial by r factorial. So you can even generalize this. Hope it is clear. The number of different 7-digit numbers that can be written, the number of different 7-digit numbers, 1, 2, 3. The number of different 7-digit numbers that can be written using only the digits 1, 2, 3, with the condition that the digit 2 occurs twice in each number. So that digit 2 should appear only twice. So that's quite a simple point. So out of the 7 positions, select any 2 positions and let 2 occupy that. And the digit 2 occurs exactly twice. So that means the remaining 5 positions, each position can be taken either by 1 or 3. Each position can be filled in 2 ways. So 2 into 2 into 2 into 2, etc. to power 5. So your answer becomes 7C2 7C2 into 2 power 5. So your answer becomes option B. So you are just selecting 2 positions out of the 7 positions in 7C2 ways, and in those 2 positions you are fixing 2, and there is no need to permute them because they are identical digits, and then the remaining 5 positions, each position can be filled either by 1 or by 3. So each position can be filled in 2 ways. So 2 into 2 into 2, etc., 2 power 5. A set contains 2n plus 1 elements. The number of subsets of set which contains at most 10 elements. At the most 10 elements. So at the most 10 elements means n elements or less. So number of subsets of the set which contain 0 elements. Okay, and number of subsets of the set which contain exactly 1 element, number of subsets of the set which contain 2 elements, and so on. Number of subsets which contain n minus 1 elements, and the number of subsets which contain n elements. So at the most 10 elements. So at the most 10 elements, that means from 0 to n elements. So we need to find the sum of this. To find the sum of this, let us call this as S. And the same S, we shall write this 2n plus 1 C0 NCR is equal to NCn minus R. So we can write this as 2n C 2n plus 1 plus 2n plus 1 C 2n plus 2n plus 1 C 2n minus 1 plus so on plus 2n plus 1 C n plus 1 2n plus 1 minus n plus 1. So that becomes n plus 2 and plus 2n plus 1 C n plus 1. So this is what we get. So now if you add these two, we get 2s is equal to, now while adding, you think of adding like this. You are not just adding like this, you are adding like this. 2n plus 1 C0 plus 2n plus 1 C1, go on up to 2n plus 1 Cn, and then start here 2n plus 1 Cn plus 1, n plus 2, and so on, 2n plus 1 C2n plus 1, which is nothing but 2 power 2n plus 1. So therefore S is equal to 2 power 2n. S is equal to 2 power 2n. So these are the number of subsets of set which contain at most n elements. So the answer is 2 power 2n. Next. The total number of ways of selecting 5 letters from the letters of the word independent. The total number of ways of selecting 5 letters from the letters of the word independent. All right. So here there is one I and n 1, 2, 3. There are three n's and d's. There are 2 d's and 1, 2, 3. There are 3 e's and there is 1 p and there is 1 t. Okay. All right. So it's like this. It's like this. Suppose let us say you have totally 11 letters totally. So there are 11 letters. Let us say, imagine like this. Suppose there are some 11 chocolates here. I assume that there is 1 chocolate of one brand and 3 chocolates of another brand and 2 of another brand and 3 of another brand, 1 of one more brand and 1 of yet another brand. So these are the varieties. Out of this, you are asked to take exactly 5 of them. You are asked to select exactly 5 of them. So is it possible for you to take 5 chocolates of the same brand? No, the stock is not there. Not possible. Is it possible to take 4 chocolates of one brand and 1 chocolate of another brand? Even that is not possible because it's not available. But you can take 3 of one brand and 2 of another brand. So 3 of one kind, 3 identical, 2 identical is what you can select. 3 identical, 2 identical. This is what you can do. In that case, If you want to take 3 identical, from these 2 varieties, you select any one variety. Having selected one variety, take all the 3 out of that. And 2 identical, you need to take only these varieties, because this is the only variety which has, so here 3 identical and 2 identical. So from this you can take one variety. Here one point is there actually. See, out of these 2 varieties, if you take one variety, one more variety is always left out, and from that you can always take 2. So that means from these 2 varieties, again you can take one variety and take 2 out of it. Take 2 out of it. So out of these 2 varieties, you are taking 3 objects, and of the remaining variety and this variety, you can take 2 objects. So that can be done in 4 ways. Next, 3 identical, 2 distinct. 3 identical, 2 distinct. So from these 2 varieties, you can take one variety and take 3 out of that. And when you do that, we are left with 5 more varieties. Out of 5 varieties, select any 2 varieties and take 1 each. So 3 identical, 2 distinct is fine. Next is 2 identical, 1 distinct. This you can do. So to do this, out of these 3 varieties, you select any 2 varieties, which is 3C 2 ways, and from that, from these 3 varieties, you select any 2 varieties and take just 2 out of each, so that you get 4. And then of the 6 varieties, 2 varieties are gone, 4 more varieties are left. Out of 4 varieties, take any one variety and take 1 out of that. So 2 identical, 1 different will come, right? And one more possibility is you can take 3 identical, 2 identical, 3 distinct. You can take 3 identical, you can take 2 identical and 3 distinct. Like that also you can take. You can use coefficients method also, but a simple problem can be done like this also. 2 identical, 3 distinct. Out of these 3 varieties, select any 2 varieties and take 2 out of that. Take any one variety, take any one variety, because you are just taking 2 identical, and from that you take 2. So out of the 6 varieties, 1 variety is gone, and we are left with 5 more varieties. Out of the 5 more varieties, select any 3 varieties and take 3 out of that. And then you can take 3 identical, 2 distinct is all 5 distinct. All 5 distinct. This also you can do. So if all the 5 distinct means out of 6 varieties, take any 5 varieties and take 1 each. So your final answer is the sum of all this, which you can simplify. This is 10 into 3, 30, and this is 3 into 4, 12, and this 10 into 3, 30, and this is 6. The sum of all this will be your required answer. The number of zeros at the end of 100 factorial. See, the greatest exponent of a prime factor p in any n factorial, the greatest exponent of a prime factor p in any n factorial. So basically this is step of n by p plus step of n by p square plus step of n by p cube and so on. The greatest integer function, the floor function, what you called floor function. All right. So this is the thing, and if you consider 100 factorial, see, if you want to find out the number of zeros at the end of 100 factorial, if you can, if you find out the number of 2's, that is the greatest exponent of 2, and if you also find out the number of 5's, that is the greatest exponent of 5, the exponent of 5 will be small, much lesser than the exponent of 2. So the number of 2's are actually every second number gives at least one 2. Only every fifth number gives at least one 5. So therefore, the number of 2's are much higher than the number of 5's. So whenever if you do the prime factorization, and if you take 1 5 and 1 2, and if you multiply, you get 1 0. Only thing is, for every 5 there should be a supply of 2, but essentially the supply is much higher. So therefore, it is the question of finding the number of 5's instead of finding the in place of finding the number of zeros. So the number of 5's will be as many as the number of zeros that you get. So it is essentially finding the number of 5's. So that is to get that. So 100 by 5 plus 100 by 5 square plus 100 by 5 cube and so on. So this is 20 and this is 4, this is anyway 0. So you have 24 5's. So when you do the prime factorization, assume that 100 factorial has been multiplied, you have factorized it completely, every number is either itself a prime or a product of primes. That is the fundamental theorem of arithmetic. So because of that, when imagine that 100 factorial has been prime factorized completely, and when you do that, the 5 will have the exponent 24, because we can as well say that 2 will have a much higher number than 24. For every 5 there is a 2, such that 5 into 2 will give 1 0. So as many 5's are there, so many zeros are there. So the number of zeros are 24. The number of ways in which 3 numbers in AP can be selected from 1, 2, 3, etc. n. 1, 2, 3, etc. n. Now let us consider 2 cases. Let us say if n is even, let us say n is equal to 2k. N is equal to 2k. So in that case, we will write 1, 2, 3, etc. 2k. Okay. So when you have 1, 2, 3, etc. 2k, there will be k numbers which are even, k even numbers will be there, and there will be k odd numbers. Now, typically when you are selecting 3 numbers to form an AP, the first and the third number should be both even or both odd. So whenever you select the 2 endpoint n numbers, the middle number, there is a unique number such that all the 3 will form an AP. See, for example, you have, I'll just show you one example. Let us say you have, let us say 1, 2, 3, 4, 5, 6, 7, 8 or whatever, 9 like that, or 10. And suppose you select any 2 even numbers. Let us say if you select any 2 even numbers, let us say 2 is selected, and let us say you take 8. Now, for the selection of 2 and 8, there is a unique number 5, such that 2, 5, 8 forms an AP. So, when you select the 2 end numbers, the middle number comes and sits there. That's a unique number. So, it's a question of selecting 2 even numbers or 2 odd numbers for the end positions. So 2 even numbers, k even numbers, out of that 2 even numbers, and are k odd numbers. So kc2 into kc2, which is 2 into kc2. This is 2 into n by 2 c2. Next. Now suppose suppose n is let us say odd. If n is odd, suppose n is odd. So in that case, if n is odd, then in that case we have, and let n is equal to k plus 1. So the odd number, there will be k plus 1 odd numbers and there will be k even numbers. Odd numbers are 1 more than the even numbers. So it is the question of selecting any two odd numbers or two even numbers. So it is k plus 1 C2 plus k C2 or the total number of ways. So in this case, this will be k is what? N minus 1 by 2, n minus 1 by 2 plus 1 C2 plus k is n minus 1 by 2 C2. So this you get n minus 1 plus 2, which is n plus 1 by 2 C2 plus n minus 1 by 2 is the total number of ways in which you can do this. Now, so in the case all the options are being asked for when n is even. So when n is even though it is asked for n is even, I have done both the cases. You can just simplify this for your current purpose of getting the answer. So this is 2 into n by 2 into n by 2 minus 1 by 1 into 2. So that becomes n into n minus 2 by 4. So this is n into n minus 2 by 4 will be the number of APs that you get when n is even, and these are the, if you simplify this, you get one answer. This is in the case when n is odd. Anyway, that is not asked now. So this is the thing, right? Now let us see the next one. There are 10 points in a plane which of which no 3 are collinear and some 4 points are concyclic. The maximum number of circles that can be drawn using these points. So there are 10 points in a plane of which no 3 points are collinear. So and some 4 points, but some 4 points are concyclic. So what we will say, out of 10 points, select any 3 points, and to get the circles, and then these 4 points are not 4C3 points, 4C3, this includes 4C3 circles, which in fact is just one circle. So your answer should be 10C3 minus 4C3 plus 1, and you can just simplify this. This is 10 into 9 into 8 by 1, 2, 3 minus 4C3 is 4 plus 1. So you can just simplify this to get your final answer. Which is 117. So your answer is, I repeat once again, there are 10 points and simply select any 3 points. So that can be done in 10C3 ways. 10C3 contains some selections of 4C3 selections. That means as if there are 4 circles, but they are not 4 circles, that is only one circle. So 10C3, it includes 4C3 which you have to remove, but when we remove that one circle also is removed, just add 1. So that becomes 117. All right. The total number of 9-digit numbers which have all different digits. The total number of 9-digit numbers which have all different digits. So it's a question of filling up of 9 blank spaces. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now it's a question of filling up of 9 blank spaces and which have all different digits. Obviously you can't place 0 here. So the first blank space can be filled in 9 ways. But then the second blank space also can be filled in 9 ways because it should have all different digits. So the digit that has been used here, the total number of 9-digit numbers which have all different digits, all right. So if all the digits have to be different, so it is a question of filling up of 10 positions, 10P9. 10P9 contains the cases where 0 comes in the first place. So how many numbers have 0 in the first place? Put 0 in the first place, and then there are 9 digits and 9 factorial. So your answer is 10P9 minus 9 factorial, quite a simple direct problem. So it becomes 9 into 9 factorial. The most interesting question actually, when I read the question, I thought like this, it's no 2 consecutive digits are same. So in that case, the first blank space can be filled in 9 ways because 0 can't come. No 2 consecutive digits should be same. So the second blank space again can be filled in 9 ways. because now 0 can come, and the next blank space again can be filled in 9 ways like that. So if no two consecutive digits are same, but here it is just a direct problem. Next. 10 different letters of an alphabet are given. Words with 5 letters are formed from these given letters. Then the number of words which have at least one of the letters repeated. So 10 different letters of alphabet are given. From the total number of words where there is repetition, from the total number of words with 5 letters are formed from these given letters. The number of words which have at least one letter repeated. From the total number of words, if you subtract those words where there is no repetition, the rest are all the cases where there is at least one letter repeated. So it's a question of filling up of 5 blank spaces. Question of filling up of 5 blank spaces. The first blank space can be filled in 10 ways, etc. 10 power 5. 10 power 5 are the total number of ways, repetitions, no repetitions and everything. Out of this, if I subtract the cases where there is no repetition, which is 10p5, the rest are all the cases where there is at least one repetition. And I am not doing the simplification. You can just do the simplification and match it with one of these things. So I repeat once again, the total number of words minus the number of words where there is no repetition. The rest are all the words where there is at least one letter repeated. 20 persons are invited for a party. In how many different ways can they and the host be seated at a circular table if the 2 particular persons are to be seated on either side of the host? See here, our host said 2 particular fellows, Mr. A and Mr. B, sit on either side of the host, and remaining 18 people can sit anywhere. So you have 21 seats around the table basically, and A, H, B, you consider them as one packet or one unit, and remaining 18 people as 18 units. So total number of units are 19. 19 units can be permuted among themselves circularly in 18 factorial ways. And wherever this packet comes, A and B can be interchanged among themselves in 2 factorial ways. So your answer is 18 factorial into 2 factorial. So 2 into 18 factorial. I repeat, A, H, B, the host, Mr. A, Mr. B, these two are 2 particular people as one unit, and the remaining 18 people as 18 units. Total number of units are 19. 19 units can be permuted circularly in 18 factorial ways. And those 2 people, A and B, can be interchanged among themselves in 2 factorial ways. The number of subsets of a set of 2m elements, if the number of elements in each subset is greater than or equal to half the number of elements given. So it is similar to the problem that we have done already. See, the number of subsets, the set contains 2m elements. Each subset should have elements greater than or equal to half the elements in the given set. So 2 greater than or equal. So subsets containing m elements exactly half or even greater, 2mc m plus 1 and 2m m plus 2 and so on, 2mc 2m. So the question is the number of subsets of a set of 2m elements. If the number of elements in each subset is greater than or equal to half the number of elements of the given set, greater than or equal to half the number. So half the number is m or even more than that, m plus 1, m plus 2 and so on up to 2m. We need to just get the sum of this. So to get this, we apply that NCR is equal to NCN minus R, so that we get 2mcm again, here 2mc m minus 1, applying NCR is equal to NCN minus R. We have 2mc m minus 2 plus so on plus 2mc 0. So this is, if 2s is equal to, just add like this. So this much we let us add, 2mc 0 plus 2mc 1 etc., 2mc m minus 1, 2mc m plus 1 and so on, 2mc 2m. this value is 2 power 2m plus this 2 MCM. So S is equal to half into 2 power 2m plus 2 MCM. So our required answer is half into 2 power 2m plus 2 MCM. That becomes option D. Okay, so let us see the next problem. You can just pause the video and make a note of it. All right. Let x1, x2, etc. xk be the divisors of the positive integer n, including 1 and n. If x1 plus x2 plus so on plus xk, x1 plus x2 plus so on plus xk is equal to 75, then we want sigma 1 by xi, I ranging from 1 to k, this value we want. So that means what we want is 1 by x1 plus 1 by x2 plus so on. Right. Now, to get this, consider, it's a very nice question, consider 75 into 1 by x1 plus 1 by x2 plus so on plus 1 by xk. Now you see, because x1, x2, etc. xk are the divisors of 75, are the divisors of n. So what I will, you just consider n into, sorry, they are divisors of n and not 75. All right. So consider n into this much. x1, x2, etc. xk are the divisors of n. When n is divided by x1, you get one divisor among the other divisors. See, for example, you take any number, let us say 48. For this number, there are several divisors. For example, you can say 48 is there, 4 into like this, and this is 4 into 2 into 4 into 4 into 3. You can say 2 power 4 into 3 power 1. Okay. So these are all, several divisors are there. For this number, there are 10 divisors, right? Now out of this, suppose 3 is one divisor, let us say. So when I write 48 by 3, what I get is 16, which is again a divisor, one of those xi's. So n by x1 could be some x5 or x6 or like that. N by x2 could be some other xi, etc. N by xi, xk will be some other xi. So n by x1, x2, etc. This will become again x1 plus x1 plus x2 plus x3 plus 1 plus xk. It need not be in this order. It can be any order. So it is more correct if you write simply xi, I ranging from 1 to n, 1 to k. So it is good to write like this, because we don't know in what order they come. So this becomes again the same thing, right? So therefore, this value is 75. If this is given, so therefore this value is 75. Right? So therefore, you want what? This one. So therefore, 1 by x1 plus 1 by x2 plus so on plus 1 by xk is equal to 75 by n. So 75 by n is your answer, option B. It's an excellent problem actually. If you consider n into this, each n by x1 can be 1 xi, n by x2 can be 1 xj, 1 by x3 can be 1 xk, and so on. So essentially you get the same divisors in different order. So it's again the same sum again, and therefore it is equal to 75. If n objects are arranged in a row, the number of ways of selecting 3 of these objects as no 2 of them are selected. So let us say you have n objects. See, here we use bijections. The concept of bijection is basically it's like this. We establish a particular relation for what we want and what has to be done, and because of that the number of ways in which this can be done and the number of ways in which this can be done are same. There is a bijective relation, and therefore if instead of counting what is required, you can count something else and say that the number of ways in which it can be done in so many ways. See, the problem, the thing is here, let us say you have, let us say n objects, 1 2 3 4 5 etc, n minus 3, n minus 2, n minus 1, n. Now if you want to select, these n objects are arranged in a row, selecting 3 of these such that no two of them are consecutive. So for that you simply cut off the last 2. From the remaining n minus 2, select any 3. Now when you select the remaining from the remaining n minus 2, select any 3, that can be done in n minus 2 C3 ways. Imagine adding 2 to the highest number, 1 to the next highest number and leave the least. The resulting selections are the required selections. So the number of ways, the bijection rule here is the number of ways of selecting any 3 numbers from the first n numbers which are placed linearly such that no 2 of them are consecutive is same as the number of ways of selecting any 3 numbers from the first n minus 2 numbers without any condition. Because when you consider adding 2 to the highest number, 1 to the next highest number and leave the least, resulting selections are the required selections. Because the method that I am giving you right now is scalable. You can, instead of just 3, you can consider for any 4 or 5 or in fact any r. Suppose you want to select any 4 numbers such that no 2 of them are consecutive, cut off the last 3. From the remaining n minus 3, simply select any 4. Imagine adding 3 to the highest number, 2 to the next highest number, 1 to the next highest number and leave the least. The resulting selections are required selections. So in general, if you want to select any r, think of ignoring the last r minus 1. So from the remaining n minus of r minus 1 numbers, select any r. Sorry. Imagine adding r minus 1 to the highest number, r minus 2 to the next highest number, r minus 3 to the next highest number, etc, etc, 1 to the last but 1 and leave the least. The resulting selections are the required selections. So the number of ways in which we can select any r numbers out of n numbers such that no 2 of them are consecutive is n minus r plus 1 cr. So this is the general formula in which this can be done. So very good, very useful formula. You can make a note of this. So the answer in this case is simply n minus 2 C3. There are other elementary ways to do this problem, of course, but I am giving you a more scalable method using bijections. So the bijective principle is simple here. The number of, I repeat once again, the number of ways of selecting any 3 numbers out of n numbers which are placed linearly such that no 2 of them are consecutive is same as the number of ways of selecting any 3 numbers in the first n minus 2 numbers without any condition. Sorry. In the same way, so let us say y 10 sides, we will just consider any number of sides. Suppose there are n points around a circle. Etc. There are n points around a circle, let us say. And let us say if you want to select, okay, any r points such that no 2 of them are consecutive. Basically, the problem here says that the same problem, see the question. From the vertices of a regular polygon of 10 sides, the number of ways of selecting 3 vertices such that no 2 vertices are consecutive. So it is the question of selecting. So it's like this. Imagine like this, there are n people who are sitting around a circular table. Suppose there are n people who are sitting around a circular table and you want to select any r people such that no 2 of the selected people should be consecutive. So for that, this can be done as a corollary to the last case that we have done. So you just imagine one fellow, any randomly taken person, any arbitrary person, let us call him John. Imagine that these n people are sitting around the circle holding their hands, and it's a human chain, let us say. Now, number of selections where John is present, number of selections where John is present. If John is to be present, his neighbors can't be present. Remove John and his neighbors from the ring. Ask John to sit here, and the neighbors are thrown out. Now we have removed n minus 3 people, and the remaining n minus 3 people are now placed as though linearly, because now 3 people are removed, the circle is broken, it's no longer circular. The remaining n minus 3 people are now placed as though linearly, of whom I have to select any r minus 1 because John is already present here. So the remaining r minus 1 people, such that no 2 of them are consecutive. I repeat once again. These n people are standing around a circle holding their hands. This is a circular arrangement. Now, we want to select any r people such that no 2 of them are consecutive, in that John should be one of the persons. Now, of the selected r people, John should be present. That is the case we are doing now. If John has to be present, obviously because no 2 of the selected people should be consecutive, his neighbors cannot be taken. So John and his neighbors, you just pull them out of the circle. Keep John here, the 2 neighbors, you send them out. Now when you remove 3 people from the ring is broken. It's no longer circular. The remaining n minus 3 people are now placed as though linearly, of whom we have to select any r minus 1 because John is already here, such that no 2 of them are consecutive. So we have the formula in the last case that it is n minus r plus 1 cr. This formula can be used now because you have broken that circle and then doing this. So n minus 3 minus of r minus 1 plus 1 c r minus 1, which becomes n minus r minus 3 plus 1 plus 1, so minus 1. So n minus r minus 1 c r minus 1. These are the number of cases where John is present. Next, the number of selections where John is not present. The number of selections where John is not present. So we don't want John now. Remove John and throw him out. Now when you have removed one person, we are now left with n minus 1 people in the ring. The ring is broken basically. It's no longer circular. The remaining n minus 1, it's no longer circular. The remaining now n minus 1 people are now placed as though linearly. These n minus 1 people are now placed as though linearly, of whom I have to select any r such that no 2 of them are consecutive. So same earlier linear formula only, n minus r plus 1 cr, which is n minus r cr. So the total number of ways are this plus either this or this can happen. This is true with regard to any John basically. So John is basically arbitrary. So with regard to any person, the same thing happens. So therefore the total number of ways are n minus r minus 1 c r minus 1 plus n minus r cr. These are the total number of ways in which we can do this. So in this particular problem, I have given a general formula for you, but you can just plug in those numbers. N is equal to 10 and r is equal to 3 because you are selecting 3 vertices. So if you do that, n is equal to 10 and r is equal to what? 3. Minus 1 c3 minus 1 plus 10 minus 3 c3, which becomes 6 c2 plus 7 c3. So 6 c2 is 15 and 7 c3, 7 into 6 into 5 by 1, 2, 3, which happens to be 35. So 35 plus 15 becomes 50. So the required answer is 50. This problem, of course, if you want, you can do it by an elementary method, not a problem. But the question is, I have given a more general formula. If the numbers n and r are large, then elementary methods doesn't work. They are not scalable approaches. So you have a general mathematical structure in place for this kind of things. And this has been as a corollary to the number of things that we have done for linear arrangements. This has linear selections. This is a case that comes out of that. Okay. Now, see, one thing, selections basically at our level of within the gamut of our syllabus, there are two things for selections. When selecting any number of things, when P things are alike of one kind, Q things are alike of a second kind, and R things are alike of another kind, which is P plus 1 and Q plus 1 and R plus 1 minus 1, taking at least one thing. So that is one case, one thing. Selecting any number of things when P are alike of one kind, Q are alike of second kind, and R are alike of another. One another thing is selecting a particular number of things. Let us say there are 10 identical white balls, 10 identical black balls, and 10 identical red balls. From this, you want to select, let us say, exactly 10 balls in whatever the combination, or you want to select exactly 15 balls. So like that. So that is one variety where we use, again, it's a bisection. Basically, the coefficient of what you say is basically a bisection. The number of ways in which this can be done and the coefficient of an expression there are just the same. So n are identical and 2n plus 1 are distinct. So the number of ways of choosing n objects, of which n are identical and 2n plus 1 are distinct. So how do we go about this? n objects, n are identical. We have to select n objects. To select n objects, we have n are identical, and 2n plus 1 are distinct. So basically, in this case, if you want to select all the n distinct objects, you want to select all distinct objects, you can do that. So that can be done in 2n plus 1 cn ways. Or if you want to select n minus 1 distinct objects and one identical object from this can be done in just one way. And if you want to select n minus 2 distinct objects and so on, you can take 0 distinct objects until you can take all n identical objects. So it is essentially finding the sum of these. So it is again the same thing, NCR is equal to NCN minus R. To n plus 1 minus n plus 1. So that becomes n plus 2 plus 2n plus 1 C n plus 3 and so on plus 2n plus 1 C 2n plus 1. So if you add these two, 2s is equal to, like this, if you add up to n and then n plus 1 so on up to 2n plus 1. So it becomes 2 power 2n plus 1 and therefore s is equal to 2 power 2. So answer is 2 power 2n. So essentially the same thing, right? Understood. Right, next. The number of ways in which 2n things of one sort, 2n things of another sort and 2n things of a third sort can be divided between two persons so that each person has 3n things. So it's a question of there are totally 6n things. Out of these 6n things, you have to select 3n things and 3n things are to be given to one person. So the other person will automatically take the remaining 3n. So it is exactly the coefficient of x to the power of 3n in the expansion of 1 plus x square plus so on plus x to the power of 2n whole cube. So because there are 3 varieties, so it is finding the see, it is the same thing that I have said, I will repeat once again. If there are n things of one kind, another n things of another kind, another n things of another kind. From these 3 n things, let us say if you want to select exactly a particular number of objects, then it is coefficient of that particular number, x power that particular number, right. So this is the coefficient of x to the power of 3n in the expansion of 1 minus x to the power of 2n plus 1 by 1 minus x whole cube. So that is the coefficient of x to the power of 3n in the expansion of 1 minus x to the power of 2n plus 1 whole cube into 1 minus x whole to the power of minus 3, which is 1 minus 3 x to the power of 2n plus 1 plus 3 x to the power of, next is 4n plus 2 is not required because we want only 3n plus 1 x to the power of 3n only. So the term next to this is not required for us, so we can just leave it in etc. into 1 minus x whole power minus 3. So when 1 is multiplied with the term containing x to the power of 3n, you get x to the power of 3n, and similarly when x to the power of 2n plus 1 is multiplied with the term containing x to the power of n minus 1, we get x to the power of 3n. So we need to find out two coefficients. So for that, coefficient of x to the power of 3n, coefficient of x to the power of 3n in 1 minus x whole power minus 3, it is n plus r minus 1 factorial by r factorial into n minus 1 factorial. So this is 3n plus 2 factorial by 3n factorial into 2 factorial. 3n plus 2 by 2. Similarly, the coefficient of x to the power of n minus 1 is n plus r minus 1 factorial by r factorial into n minus 1 factorial. Sorry. The coefficient of x to the power of n minus 1, n plus r minus 1 factorial by r factorial into n minus 1 factorial. So this is n plus 1 factorial by n minus 1 factorial into 2 factorial, which becomes n into n plus 1 by 2. So it's the final answer will be 1 into this much, the first one, which is 3n plus 1 into 3n plus 2 by 2 plus minus 3 into the second one. All right. So this is 1 by 2 into you have 9n square plus 6n plus 3n, 9n plus 2 minus 3n square minus 3n, which happens to be 1 by 2 into 6n square plus 9n minus 3n is 6n plus 2, which you can write it as 3n square plus 3n plus 1. So the number of ways in which this can be done is 3n square plus 3n plus 1. Option A comes correct. Right. Next. In how many ways can 52 cards be dealt to 4 players so that each gets, now this is distributions. Now in distributions again we have, let us say 7, 8 cases. Equal distributions, we have 2 cases, and any kind of distributions, groups and parcels we call. When blank lots are allowed, blank lots not allowed, they have totally 6 cases there. And in all these cases, the boxes are distinct and the objects can be distinct or can be identical. So this comes under equal distributions. So the question here is the number of ways in which we can distribute 52 cards to 4 players so that each gets 3 cards from 3 of the suits and 4 cards from the 4th suit. So basically there are 52 playing cards, and these 52 playing cards there are 4 suits, 13 cards each, and we have 4 players. How do we give them? we have to give equally to everybody 13 cards in such a way that let us say player A, if he gets 3 clubs, 3 hearts, 3 diamonds, then you should get the 4 cards from the remaining spades, 4 spades. Another person should get, let us say, 4 diamonds, 3 spades, 3 clubs, 3 hearts, like that. So, a set of 3 cards each from 3 of the suits and 4 cards from the 4th suit. So, to do that, first we will divide and then distribute. So, the 13 cards of each suit can be divided into sets of 3, 3, 3, 4 in 13 factorial by 3 factorial whole cube into 4 factorial. Those 3 can be permuted among themselves in 3 factorial ways. So, this becomes 3 factorial, 13 factorial by 3 factorial to the power of 4 into 4 factorial. These are the number of ways in which a suit of 13 cards can be divided into sets of 3, 4. Now, there are 4 sets like that, 4 suits that can be done in whole power 4 ways. Now, with regard to distribution, the 4 sets of 4 cards each, can be distributed to the 4 players in 4 factorial ways. Now, we are left with 3 sets of 3 cards each. 3 sets of 3 cards each. So, they can be distributed to the remaining people in 3 factorial, 3 factorial, 3 factorial, 3 factorial, 3 factorial to the power of 4 ways. So, the required number of ways is this. So, these are the total number of ways in which we can distribute the 52 playing cards among 4 players, such that each player gets 3 cards from 3 of the suits and 4 cards from the 4th suit. Five balls of different size colors are to be placed in 3 boxes. This is each box can hold all the 5 balls, the number of ways of placing the ball so that no box is empty. So, it is the question of dividing n different things, or parcels, blank lots not allowed, or parcels, blank lots not allowed. N different things or parcels, blank lots not allowed. So, the formula is r power n minus rc1 into r minus 1 to the power of n plus rc2 into r minus 2 to the power of n and so on. This is the formula for because the same thing happens in the case of bijections, onto function surjections also. So, the formula can be remembered if you are asked to find the number of onto functions. So, these are number of ways of dividing n different things into r parcels, blank lots not allowed. So, that is no box should be empty. So, in this case, in this problem there are 5 balls and placed in 3 different boxes. So, r is equal to 3 and n is equal to 5. Being I encourage all of you to go through the theory behind all these things in a nutshell once again for a deeper understanding. 3 power 5 instead of just remembering the formula. 3 power 5, 5 power 3 and r is equal to 5. So, minus 3c1 into 2 power 5 plus 3c2 into 1 power 5. This happens to be 150. I think this question with the same numbers, at least twice it has come in the ID exam. As far as my memory goes, at least 2 times, it could be even 3 times, I am not sure, but 2 times at least it has come. Same question and surprisingly with the same numbers. Right. The number of non-negative integral solutions of x to the power 20. So, it is a question of finding the coefficient x to the power 20 in the expansion of 1 plus x square, etc. x power 20, maximum 20 whole cube into 1 plus x power 4 plus x power 8 plus like that you can do. This is one method you can follow. The other method is by distributions. This is by selections. If you want to do it by distributions, you can do that also. Probably that would be more easier if you do that. if you use the distributions, the simplification could be little smaller instead of selections. This kind of problems you can use selections or you can use distributions, any of these two. Selections is basically giving, distributions, selections is basically taking, and distributions is basically giving. These two are two different things, but these problems can be done either that way or this way. So here, if you want to consider it as a distribution, and remember distribution is always better than selection, it's more simpler always. And if I put x4 is equal to 0, if x4 takes the value 0, then we have x1 plus x2 plus x3 is equal to 20, and number of non-negative, it is a question of distributing 20 identical apples to 3 people, blank lots allowed. So n plus r minus 1, so the formula is n plus r minus 1 factorial by n factorial into r minus 1 factorial. So right, so this is, so and the 20 apples are to be distributed, identical apples are to be distributed to 3 people such that blank lots are allowed. So this can be done in 20 plus 3 minus 1 factorial by 20 factorial into 2 factorial, 22 C2. Now if x4 is equal to 1, when x4 takes the value 1, then x1 plus x2 plus x3 will become 16. In that case, the number of ways in which you can, this is the question of distributing 16 identical apples among 3 boys allowed. So that is 16 plus 3 minus 1 factorial by 2 factorial, which is 18 factorial 18 C2 basically. And if x4 is equal to 2, x4 is equal to 2, so that becomes 8, and so x1 plus x2 plus x3 is equal to 20 minus 8 will be 12. So that will be n plus minus 1 factorial by 12 identical apples are to be distributed to 3 people, so that any boy can receive any number of apples. And if x4 is equal to 3, you can have x1 plus x2 plus x3 is equal to, x4 is equal to 3 means 12, so 20 minus 12 is 8. So it is a question of distributing 8 identical apples. So 8 plus 3 minus 1 factorial by 8 factorial into 2 factorial. So this is 10 C2. And if x4 is equal to 4, so that becomes 16. So x1 plus x2 plus x3 is equal to 4. So that becomes n plus r minus 1 factorial by r n factorial into r minus 1 factorial. So this is 6 C2. And if x4 takes the value 5, so all the 20 are gone here. So we have x1 plus x2 plus x3 should be equal to 0, and this is just one case. So the question is, the answer is the sum of all this, and if you simplify, one of them will match, right? Now let us see. You can also do the coefficient x to the power 20 in the expansion of 1 plus x square etc. x to the power 20 whole cube into 1 plus x power 4 plus x power 8 plus x power 12 plus x power 16 plus x power 20. You can do that also. Again, the same things will come. The number of non-negative integral solutions of x1 plus x2 plus x3 plus x4 less than or equal to n, and is a positive integer. So for a non-negative integer x5, for a non-negative integer x5, we should have x1 plus x2 plus x3 plus x4 plus x5 is equal to n. So this is the point here. x5 can be greater than or equal to 0. So to find the number of non-negative integral solutions of this inequality is same as finding the number of non-negative integral solutions of this equality. So it is the question of dividing n identical things among 5 people, non-negative, so 0 is allowed, blank lots are allowed. So it is a question of dividing n identical things into 5 parcels, blank lots allowed. So n plus r minus 1 factorial by n factorial into r minus 1 factorial, which is n plus 4 n plus 4 cn or n plus 4 cr c4, anything you can say, or n plus 4 cn also you can say. So option A is correct. The number of ways of distributing eight identical balls in 3 distinct boxes such that none of the box is empty. Again, same thing. The question of dividing n identical things are parcels. None of the box is empty. Blank lots not allowed. N identical things are parcels, blank lots not allowed. So that is n minus 1 C r minus 1 is your answer. The formula is n minus 1. See, I'll just write down n different things. N different things. I'm just writing all the formula in one shot here. N different things are groups, are parcels you can divide. Parcels means internal arrangements are not required. Groups means even the internal arrangements are required. Here blank lots allowed. So this is n plus r minus 1 factorial by r minus 1 factorial. Blank lots not allowed. It is n factorial into n minus 1 c r minus 1. So r parcels, blank lots allowed. Blank lots allowed. What happened? Blank lots allowed. So this is r power n. Blank lots not allowed. We have used this formula today, which is r power n minus rc1 into r minus 1 to the power of n plus 1 plus rc2 into r minus 2 whole to the power of n and so on. So these are 4 cases with n different things. Similarly, with n identical things, obviously you can't make groups with that, only parcels, r parcels, blank lots allowed. This is n plus r minus 1 factorial by n factorial into r minus 1 factorial. And when blank lots not allowed, it is n minus 1 cr minus 1, right? So n minus 1 cr minus 1. So in this case, n is equal to 8. 8 minus 1 cr minus 1, 3 distinct boxes. C2, 3 minus 1. So you get 7 C2, 21. Answer is 21. Option B. So these are the 6 formulae in the case of this kind of distributions, which you may prefer to remember them. The total number of ways in which n square number of identical balls can be put in n numbered boxes such that the ith box contains at least I number of balls. So that means what? Now there are we put n numbered boxes. So there are n boxes, let us say there are n boxes. N boxes are there. And this is box 1, 2, 3, 4, etc. n. The ith box should contain at least I number of balls. So that means you put one ball here in this, you put 2 balls here, at least minimum 3, 4, etc. n balls. So initially, because they are identical objects, this distribution there is no problem. But if the objects are distinct, then there will, you can't do this thing. Think of it why you should not do it. So here, out of n square objects, this 1 plus 2 plus so on plus n are already distributed. So that means this is n square minus n into n plus 1 by 2 has already been distributed. So this becomes 2n square minus n square minus n by 2, which happens to be n square minus n by 2. So these are remaining. These these balls n square minus n by 2 balls can be distributed in whatever the way you want. This n square minus n by 2 out of n square balls, each can be put in n numbered boxes such that the ith box contains at least I balls. So first at least one, so the minimum balls we are putting first 1, 2, 3, 4 etc. n. So that means n into n plus 1 by 2 are gone. So 2n square minus n by 2, which is n square minus n by 2 are left. Now these number of balls are distributed into n boxes. So n square minus n by 2 identical objects n parcels. Now blank lots allowed, because these remaining balls you can distribute the way you want. Blank lots allowed. So n identical things or parcels, n identical things or parcels, blank lots allowed. It is n plus r minus 1 factorial by n factorial into r minus 1 factorial. So this is n square minus n by 2. In place of n you have n square minus n by 2. In place of r you have n minus 1 factorial by, in place of n you have n square minus n by 2. In place of r you have n. So this is n minus 1 factorial. So this becomes n square minus n plus 2n minus 2 by 2 c n minus 1. So this happens to be n square plus n minus 2 by 2 c n minus 1. N square plus n minus 2 by 2 c n minus 1. So option C comes correct. Okay, then you can pause the video and copy it. I'll go to the next one. The number of ways in which 15 identical mathematics books be distributed among 6 students. So n identical things, 6 people, one book and all. Blank lots allowed. Again the same formula. N identical things or parcels, blank lots allowed. So that is n plus r minus 1 factorial by n factorial into r minus 1 factorial, which happens to be n is n only, 15 only. N is equal to 15 books, 6 people. 15 plus 6 minus 1 factorial by 15 factorial into 5 factorial. So this is 20 factorial by 15 factorial into 5 factorial. So if you simplify, a number comes and that's your answer, right? So understand conceptually and remember important results and do a lot of practice. And understanding and practice are two activities which are not interchangeable. A simple understanding will not replace practice, and practice without understanding is useless. So therefore, understanding, practice, these two are essential. And when you understand and when you practice, you not only get the practice, you will also remember important results. And when you remember the important result, that has to be in the memory basically. And when you remember them, you also know the moment you recall some formula or some, you recall the whole concept, the story behind that. That is a true understanding. All the best. We shall meet in with some other topic next. Good night, all of you.